All right, people, welcome back. So today we're going to talk about solving systems of linear equations using these gadgets called matrices. So first, matrices is the plural form of matrix. So what is a matrix but a rectangular arrangement of numbers? Okay, so we'll have some rows and some columns in this little rectangle, and in each little slot we'll have a number. So this first example here is a matrix that has one row but two columns. Okay. This second one is a matrix that has two rows but just one column. Okay. This next example is a matrix that has two rows and two columns. And this last example here is a matrix that has just one row and one column. It's really just kind of a single number, right, with just these weird kind of brackets written around it. Okay, so in some sense, a matrix might be a generalization of a number in some way. So we're going to be looking at that a little bit more as we go along. So the size of a matrix is exactly this, the number of rows times the number of columns. So for example, this first one here that had one row and two columns, we would say that that is a 1x2 matrix. And this second one is a 2x1 matrix. This third one is a 2x2 matrix, and this last one is a 1x1 matrix. Okay, and so for a system of linear equations, we can use some matrices and maybe some operations on matrices to solve that system in maybe a nice, clever way. So the first thing that we're going to do is convert a system of linear equations into what they call an augmented matrix. And what does this word augmented mean? Well, it means that there's been this funny line drawn down, drawn down this matrix in between these two columns. Okay, and what exactly that line kind of stands for, well, we'll kind of get there later. For now, you can probably be fine to just think of this line as a sort of decoration that takes the place of these two equal signs in the system of equations above. So what we do is that on the left side of this little line, we'll write the coefficients going into our linear functions. So we'll always keep the x1 first on the left and then the y1 second. So up here we have 3 and minus 4. And then on the other side of the equal sign, or the line here, we'll write the constant value from the other side of the equation, which was 9. Okay, and similarly, we'll translate the other equation to the next row of this matrix. So we'll have 2 as the first coefficient for x, 1 as the coefficient for y, and minus 7 as the constant value on the other side. Okay, and we could do this same thing just for systems that have 3 variables involved. So here we have a system of equations that has 3 variables. And so we've decided to translate that one to an augmented matrix as follows. Notice that there is no y term in the second equation, so I will put the coefficient of 0 in to hold that place there. Okay. Okay. And we could also maybe go backwards. That's kind of a useful thing. If you're given an augmented matrix, say what is the corresponding system of equations. Well, I'll just read off the coefficients and then put x and y back where they belong. So I have here 3x plus 2y equals to minus 7, and 1x minus 8y equals to 3. Okay, here's the last one that's really nice. We have this matrix here. Let's see, we'll have 1x plus 0y plus 0z equals to 7. Well, we could just write that that is just x equals to 7. We also have 0x plus 1y plus 0z equals to minus 3. So I could really just write that as y equals to minus 3. And then last, we have 0x plus 0y plus 1z equals to 2. So here we have z equals to 2. Notice that this is really looks like the solution set to a system of 3 equations and 3 variables. We don't have anything to solve here, right? They're telling us right on the nose, x is 7, y is minus 3, and z is equal to 2. So matrices that look like this are kind of the ideal ones. And so we're going to do some work to turn a matrix that doesn't look like this into one that does, so that we can have the solution for the system of equations in column. And the way by which we're going to do that are these three operations that they call elementary row operations. So the three operations that you can do to a matrix are interchange two rows, multiply any row by a non-zero constant. So multiply everything by, say, 4 or 1/4 or something like that. Any number that's not zero, multiply every row or every number in the single row by that same number. Okay, and the last thing that we can do is add a multiple of one row to another row. So let's watch these guys in action now. So they've given us this first matrix here. Its first row is 3, 4, and 8, and its second row is -2, 5, and 9. So we will perform this first operation, which stands for interchange row 1 and row 2. And so when we do that, we get that row 2 will go on top and row 1 will go on bottom. So we'll have now -2, 5, and 9 on top, and 3, 4, and 8 as the second row. Okay. Okay, this next bit of notation here stands for the second operation. It says, take row 2, multiply it by 3, and then replace your old row 2 with this new one that's been multiplied by 3. So we keep row 1 the same here. That's not referenced at all here. So if I start again with this original matrix here, we have 3, 4, and 8 at the top, and -2, 5, and 9 as the second row. So now I will replace the second row with 3 times that. So the first row stays the same, and the second one becomes -6, 15, and 27. Okay, and then this last row operation here, this one reads as, take row 2 and replace it with row 2 plus -2 times row 1. So when we do this here, we're only going to multiply row 1 by -2 insofar as we are adding that to the second row. So ultimately, we will keep row 1 the same at the end of the operation. The only thing that gets altered is this row 2 over here. And it gets altered in such a way that we replace it with itself plus -2 times row 1. And the way we add is that we add column-wise. So let's watch this in action here. We have our first matrix that we started with here. Its rows are 3, 4, and 8. And his columns are, and the second row is -2, 5, and 9. Okay, so then we're going to keep row 1 the same. But in each corresponding entry of row 2, we're going to add -2 times the number above that. So here we have -2 in the first column entry of the second row. And so off to the side here, I wrote, there's that number -2. And we're going to add to it -2 times the number above it, which is 3. That gives us -8. So I'll replace that in a -2 with now -8. Okay? Okay, in the second column of the second row, we have the number 5. And so I'm going to take that number 5 and add to it -2 times the number above it, which is 4. So 5 plus -2 times 4, it gives me -3. So now I will replace this 5 with the number -3. Okay, and then last but not least, we've got the number 9 here in the bottom right entry of this matrix. And so we are going to take that number 9 and add to it -2 times the number above it, which is 8. Okay, and you can check that 9 plus -2 times 8 gives you -7. So we can replace the 9 in this entry here with -7. All right, so that is the 3 row operations. I think probably the last one is the one that's the most tricky, but you kind of get the hang of it if you just practice a little bit. So, okay, so the next thing to talk about is this thing called reduced row echelon form. So we'll say that a matrix is in reduced row echelon form if all the rows consisting of only zeros are at the very bottom of the matrix, And then for all the other rows, the first non-zero entry is a 1, which they call the leading one. So this is going from, say, left to right along the row. The first non-zero entry will be 1. Okay, the next qualification to be reduced row echelon form is that the leading one in each non-zero row is to the right of the leading one in the row immediately above. Okay, so we'll see this one in play in a minute here. And then the last stipulation that we need is that each row with a leading one has zeros above the leading one. Okay, so let's determine, is this matrix in reduced row echelon form? Well, let's see. Do all the rows consisting of only zeros live at the bottom? Yes, that's this one right down here. Then for all the other rows going from left to right, the first non-zero entry is a 1. That looks good here. Okay, and then the leading one in this row is to the right of the leading one immediately above. That's also true. Yes, it's to the right here. Okay, and then each row with a leading one is going to have zeros above the leading one. Well, there's nothing above this guy, so there's nothing to check there. But there is one thing above this one here, and it is 0. So this one does meet all of the qualifications, so we'll say, yes, this is in reduced row echelon form. Okay, how about this next one? It looks like no, because almost everything I think is satisfied. We don't have anything to check for item 1, but we do have for item 2, that is satisfied. The first non-zero entry in each row is a 1. That's good. And each leading one is to the right of the ones above it, right? So that's good too. But then item 4 is what fails here because this leading one has a number that is not 0 immediately above it. So this one is not in reduced row echelon form. Okay, and then this last one here, it looks like do we have any rows of zeros? No, so there's nothing to check for item 1. But for item 2, let's see, the first non-zero entry in each row is a 1, so that's good to go. But now, oh, item 3 has got a problem. So the leading one in the second row is to the left of the leading one above it. Well, that's the only real problem here. And notice how we might fix that problem. We can perform the elementary row operation of just interchanging the first two rows, right? And if we interchange the first 2 rows, then we get a matrix that is in reduced row echelon form. So excellent. So maybe this, what's to like about this reduced row echelon form? Well, look at this one here now. It looks like it's exactly that kind of nice matrix that we saw before that just reads off the solution to a system of equations. And so there's 2 things that we kind of haven't said yet, is that one is that we can use these elementary row operations to take a matrix that is not in reduced row echelon form and make it into a matrix that is in reduced row echelon form. And the second thing that's probably more important here is that all of these elementary row operations will preserve the system of equations that we have. So interchanging the 2 equations doesn't change their solutions, right? Multiplying one equation by a non-zero constant on both sides doesn't change its solutions, right? And this adding a multiple of one row to another row is kind of like what we were doing in the addition method of solving systems of equations. That will also not alter the solution set for the system of equations that the matrix at hand is talking about. So if we do these elementary row operations, we're able to preserve the system of equations at the same time as making it look like it's reduced row echelon form so that we can just ultimately read off the solution at the end. And so the process of doing that is what's called Gauss-Jordan elimination, and we will take that up in the next video.